The tidal truncation radius marks the outermost boundary, the true limit of the Sun's domain. Beyond this unseen threshold, its gravity loosens its hold, and you become a citizen of the galaxy. Everything rising above or stretching below the solar system, every grand structure we've spoken of, lies beyond this edge or unfolds on scales far greater than it. The local bubble spans about 1,000 light-years. The galactic halo extends hundreds of thousands more, and binding it all together, dark matter weaves an invisible framework around the Milky Way. Within these immense cosmic layers, our solar system is little more than a speck of dust. The Sun's gravitational influence fades after roughly 3 light-years, where the Milky Way's power fully takes command. Yet what lies beyond is no void. It is a vast galactic sea, alive with hot plasma, magnetic currents, dark matter clouds, cosmic rays, drifting stars, and the ancient debris of creation. We float within this immense ocean, guarded only by the fragile reach of our star. But that protection has its end. The boundary is real. The Sun's dominion dissolves there, and beyond that frontier, the galaxy itself awaits. Picture the Milky Way as a spinning disk of stars, flat, wide, packed with light. Most stars crowd near the middle, hugging that central plane where gravity holds everything tight. You would think our Sun lives there too, pressed into that cosmic flatline with all the others. It does not. Our entire solar system floats 55 light-years above the galactic midline. That is 324 trillion miles north of where the galaxy is thickest. Scientists confirmed this measurement using gamma-ray telescopes that peer through dust and gas, marking our exact position in 3-dimensional space. The data is solid. We are not where we should be. The galactic plane itself stretches 100,000 light-years across, but only 1,000 light-years thick. Think of a dinner plate. The Sun should be somewhere in that plate, but instead it hovers above the porcelain, floating in the emptiness between the table and the dish. This positioning changes everything about what surrounds us. Most people imagine space as a sphere around Earth. They think dangers and wonders spread equally in all directions. Wrong. When you look up at night toward the northern galactic pole, you are staring into a completely different neighborhood than when you look down toward the south. The structures are different. The densities are different. Even the temperature of invisible gas differs between these two directions, though scientists still argue about why. Being above the plane means we experience less radiation from the galactic center. That supermassive black hole, 4 million times heavier than our Sun, sits 27,000 light-years away. But it is also below us in that dense stellar disk. Its violence gets filtered through layers of gas and stars before reaching our floating position. Some researchers suggest this elevation protected Earth during its early years, allowing life to develop without being scorched by excessive cosmic rays. But here is what makes astronomers nervous. Our position is not permanent. The Sun does not stay at 55 light-years north forever. It moves, it oscillates, it swings up and down through the galactic plane like a weight on a spring, crossing through that crowded stellar disk again and again. We are currently moving away from the plane, heading farther north at about 4.5 m/s. The last time we crossed through the galactic plane was 3 million years ago, right when early humans started walking upright in Africa. The next time we cross will be 30 million years from now, assuming nothing massive knocks us off course first. Each crossing takes us through denser regions of space, through clouds of gas and gravitational chaos that could disturb the frozen comets orbiting at our solar system's edge. And that oscillation, that cosmic bobbing motion up and down, happens because of forces you cannot see pulling on us from above and below. Forces that never stop. Forces that treat our Sun like a toy on a string, yanking it through different layers of the galaxy, whether we want to move or not. What causes that pull? The answer gets stranger than you expect. Imagine dropping a ball through a hole drilled through Earth's center. The ball falls, picking up speed, shoots past the center, and keeps going to the other side. Then gravity pulls it back. The ball oscillates through the planet over and over, like a pendulum swinging through vertical space. Our sun does exactly this through the Milky Way. Every 26 million years, the solar system completes one full bounce up and down through the galactic plane and back again. Scientists confirm this rhythm by tracking stellar positions and calculating gravitational forces throughout the galaxy. The math is certain. We are a cosmic pendulum. Here is how it works. The galactic disk contains most of the Milky Way's visible mass. Stars, gas, dust, all packed into that flat structure. When the sun floats above the plane like it does now, all that mass below us creates a gravitational tug downward. Every star, every cloud, every particle pulls us back toward the middle. So we fall, slowly at first, then faster. We are currently moving north, away from the plane, but that motion is slowing down. Eventually, we will stop rising, hover for a moment, then plunge back toward the galactic center line. When we cross through the plane, we will be moving fast, maybe 6 millites or more, enough to shoot past the middle and out the other side. Then the same thing happens in reverse. Once we emerge below the galactic plane, all that mass above us pulls upward. We slow down, stop, reverse course, and fall back through the plane again, heading north. The cycle never ends. It has repeated hundreds of times since the sun formed 4.5 billion years ago. But something makes this motion more complex than a simple pendulum. The galactic disk is not the only thing pulling on us. Dark matter, that invisible substance making up most of the galaxy's mass, wraps the entire Milky Way in a halo extending far above and below the visible stars. This dark matter contributes about 15% additional pull to our vertical oscillation. Scientists calculated this by measuring how fast we move and working backward to figure out what forces could cause that speed. Some researchers proposed something terrifying in the 1980s. They suggested we encounter denser regions of matter every time we cross the galactic plane, and those dense patches shape the Oort Cloud, sending comets flying toward Earth. They called it the extinction theory. Major extinction events on Earth, including the one that killed the dinosaurs, seem to line up with our crossings through the galactic plane every 26 million years. The evidence looked compelling at first. Then, better dating of extinction events showed the pattern was not as clean as initially thought. The theory fell apart under scrutiny, but here is what still bothers astronomers. We do cross through different environments. The density of gas, the strength of magnetic fields, the intensity of radiation, all of these change as we bob up and down through galactic space. And those changes definitely affect what happens at the edge of our solar system. The pendulum motion means Earth has experienced different galactic neighborhoods throughout its history. Life evolved while the sun traveled through varying cosmic conditions. Some periods were calm, others violent. What waits for us on the next swing through the plane? Nobody can say for certain, but the physics promises we will find out in about 30 million years. Unless something else reaches us first, something already closing in from the void we float inside. You live inside a bubble 1,000 light years wide. The walls are made of compressed gas. The interior is nearly empty, one of the most extreme vacuums astronomers have ever detected in space. This is not a natural formation. This is a crime scene. Scientists call it the local bubble. They confirmed its existence using multiple methods, including X-ray telescopes that mapped the hot gas, defining its boundaries, and optical surveys that showed where nearby stars cluster. Every star within 500 light-years of Earth sits on the surface of this bubble, not inside it. We float in a cosmic cavity, carved by violence. The inside of the bubble contains about 1,000th of an atom per centimeter. That is 10 million times less dense than the air you breathe. For comparison, the best laboratory vacuum humans can create is still 10,000 times denser than a typical interstellar cloud, which itself is thousands of times denser than the local bubble. This void is absurdly empty. But here is what makes it strange. The gas inside is hot, not warm, hot, about 1 million degrees Kelvin. Meanwhile, the local interstellar cloud immediately surrounding our solar system is merely warm at 7,000 degrees, with a density of 3 par, 10 of an atom per centimeter, two completely different environments pressed against each other. How does gas reach 1 million pause in the middle of nowhere? Only one thing produces that kind of heat: supernova explosions. Multiple supernovae, massive stars detonating in sequence, each blast feeding energy into the expanding cavity, heating the interior to temperatures that would vaporize anything solid instantly. Astronomers traced the evidence backward. They studied the motion of nearby star clusters and calculated when massive stars in our neighborhood would have exploded. The timeline pointed to 10 to 20 million years ago. Not one supernova, but several, possibly as many as 15 or 20 separate detonations. Each explosion added energy to the bubble, pushing its walls outwards, sweeping up gas and dust, creating the void we now inhabit. Think about what that means. Our solar system was already here when those stars exploded. Earth existed. Life thrived in the ocean, and somewhere out in our galactic neighborhood, massive stars reached the end of their fuel supplies and detonated one after another in a cosmic chain reaction. Each blast sent shockwaves expanding at thousands of miles, and each one heated the surrounding gas to millions of degrees. The bubble grew larger with every explosion. We survived it, barely. The shockwaves weakened as they traveled outward. By the time they reached us, assuming we were near the edge of the forming bubble, the violence had dissipated enough not to destroy Earth's atmosphere. But the evidence suggests something more terrifying. We might have been inside the bubble as it formed, caught in the expanding cavity, bombarded by radiation and high-energy particles for millions of years. Scientists recently discovered we are in the process of emerging from the local bubble. Our trajectory will take us out of this void in several million years, assuming we will not encounter another dense cloud first. But the bubble itself is not finished. It continues expanding, even now, though more slowly than during the initial blasts. The walls push outward into surrounding space, compressing gas at the edges, potentially triggering new star formation. And here is the part that should keep you awake at night. Every star has a lifespan. Every massive star eventually explodes. The local bubble is surrounded by young, bright stars in a structure called Gould's Belt. Some of those stars will go supernova in the future. The crime scene is not cold yet. The killers might strike again. 15 massive stars died to create the space you call home. Each one burned brighter than our sun ever could, lived fast, exhausted its fuel in just a few million years, then exploded with more energy than our sun will produce in its entire 10 billion year lifetime. These were not distant events. These happened in our neighborhood. The best candidate for triggering the local bubble is a group of stars astronomers called the Scorpius-Centaurus Association. This collection of massive, hot stars sits about 400 light-years away, right on the edge of our bubble. Computer simulations confirmed that a cluster of supernovae in that location could carve out a cavity matching the size and shape of the local bubble we observe today. Here is how a supernova creates a bubble. A massive star, maybe 20 or 30 times heavier than our sun, fuses hydrogen into helium in its core, then helium into carbon, carbon into oxygen. The fusion continues up the periodic table, creating heavier and heavier elements. But when the core starts fusing iron, the process stops producing energy. Instead, it consumes energy. The core collapses in less than a second. Matter falls inward at nearly a quarter of the speed of light. The collapse happens so fast that the outer layers do not have time to react. They hang in space for a moment, suspended, while the core implodes beneath them. Then the core bounces. The rebound sends a shock wave, exploding outward through the star's outer layers at thousands of miles frets. The star tears itself apart. The explosion releases more energy in a few seconds than 100 billion normal stars produce in the same time. That energy blasts outward in all directions, heating surrounding gas to millions of degrees, accelerating it to supersonic speeds. A supernova remnant expands like a cosmic bomb crater, growing larger every year. Now imagine 15 or 20 of these explosions happening in the same region of space. over 10 million years. Each blast adds energy to the expanding cavity. Each one pushes the bubble walls farther outward. The combined effect creates a structure far larger than any single supernova could produce. This is called a superbubble. The violence does not stop at the explosion. The shock waves from multiple supernovae collide with each other and with the surrounding interstellar medium. Where these shock fronts meet, they compress gas into dense sheets. These compressed regions sometimes collapse under their own gravity, triggering new waves of star formation. The cycle repeats. Massive stars form, live fast, explode, create more bubbles, trigger more star formation. Scientists found physical evidence these explosions affected Earth. The proof sits in deep ocean sediments. When researchers drilled cores from the ocean floor and analyzed the layers, they discovered elevated concentrations of iron-60, a radioactive isotope that does not form naturally on Earth or in our solar system. The only known source is supernova explosions. The iron-60 peaked twice, once about 1.7 to 3.2 million years ago, and again about 6.5 to 8.7 million years ago. Both peaks correspond perfectly with the time our solar system would have crossed through debris clouds from the supernovae that created the local bubble. The radioactive atoms fell from space, settled in the ocean, and stayed there as evidence. The proof is buried in mud at the bottom of the sea, and here is what troubles astronomers who study this. We do not know exactly where the solar system was positioned when those explosions happened. We might have been near the edge of the forming bubble, relatively safe, or we could have been much closer to the detonations, exposed to far more radiation than Earth's magnetic field and atmosphere could easily handle. The radiation levels could have influenced mutation rates and life on Earth, possibly accelerating evolution during those periods. We survived, but what changed inside us because of it? Nobody knows yet. Deep beneath the Pacific Ocean, buried in layers of mud that have been accumulating for millions of years, lies proof that our solar system crossed through a supernova debris field. The evidence is not theoretical. You can hold it in your hand if you drill deep enough. It glows with radioactive decay. The isotope is iron-60. This form of iron contains 26 protons and 34 neutrons in its nucleus, making it unstable. It decays with a half-life of 2.6 million years, releasing radiation as it transforms into more stable elements. Iron-60 does not form on Earth naturally. It cannot be produced by normal stellar processes in our Sun. The only way to create significant quantities of this isotope is in the heart of a supernova explosion. Scientists discovered the iron-60 by accident in the 1990s while studying deep-sea ferromanganese crusts. These formations grow incredibly slowly on the ocean floor, accumulating layers of metal compounds at rates of just a few millimeters every million years. By slicing these crusts into thin layers and dating each layer using other radioactive isotopes like beryllium-110, researchers could create a timeline showing how the chemical composition of material falling from space changed over millions of years. Some layers contained normal amounts of iron. Others had iron-60 concentrations far above background levels. The spikes were sharp, indicating the iron-60 arrived during specific time periods rather than continuously. When scientists dated those layers, they found two distinct peaks. The first occurred roughly 2 million years ago, give or take a few 100,000 years. The second happened around 7 million years ago with similar uncertainty. The numbers matched perfectly with predictions about when the supernovae that created the local bubble would have expelled their debris, and when Earth would have passed through that expanding cloud of radioactive material. The fit was too precise to be coincident. The scientists had found physical proof that Earth traveled through the aftermath of nearby stellar explosions. But iron-60 is not the only isotope. Researchers later found manganese-53 in the same layers, another element produced primarily in supernovae. They discovered plutonium-244 as well, which also cannot form on Earth naturally. The multiple isotopes strengthened the case. These were not measurement errors or contamination. The radioactive atoms genuinely fell from space during those specific periods. The discovery answered some questions, but raised others. How much radiation did Earth receive during those passages through supernova debris. The iron 60 itself is not particularly dangerous because it arrived in tiny amounts, a few atoms here and there spread across the entire planet. But the presence of iron 60 indicates the whole debris cloud passed over Earth, and that cloud would have contained other particles too. High-energy cosmic rays, gamma radiation, X-rays. All of this would have bombarded Earth's atmosphere. Some scientists suggested this radiation could have affected life on Earth, increased mutation rates, disrupted ecosystems, possibly even contributed to extinction events if the radiation dose was high enough. But the evidence remains unclear. Life obviously survived. No major extinction events line up perfectly with the iron 60 peaks. Either the radiation was not intense enough to cause catastrophic damage, or Earth's magnetic field and atmosphere shielded the surface effectively enough to prevent disaster. More recently, researchers found similar iron 60 deposits in Antarctic snow, on the Moon, and in cosmic dust collected by high-altitude aircraft. The isotope continues raining down on us even now, though in smaller amounts than during the peak periods. This suggests we are still interacting with the remnants of those ancient explosions, still passing through the outer edges of the debris field, even millions of years later. The radioactive evidence proves something important. Earth is not isolated. We travel through the galaxy, and the galaxy leaves its marks on us. The supernova explosions that created our local cosmic environment did not just happen somewhere far away. They touched Earth directly. Their fingerprints remain in our soil, in our oceans, possibly even in our DNA, if the radiation influenced evolution during those periods. We are, in a very real sense, made from the ashes of dead stars, and we carry proof of the violence that shaped our neighborhood in the radioactive atoms still decaying in Earth's crust. Right now, Earth is flying through a cloud, not a weather cloud, but an interstellar cloud made of hydrogen, helium, and trace amounts of heavier elements. This cloud surrounds our entire solar system, wrapping us in a cocoon of warm gas that extends several light years in every direction. Scientists call it the local interstellar cloud, and it is moving. The cloud itself measures about 30 light years across, though its exact boundaries remain fuzzy because gas densities gradually decrease toward the edges rather than stopping abruptly. The temperature sits around 7,000 degrees Kelvin, which sounds hot but qualifies as merely warm by interstellar standards. The density measures 0.3 of an atom per cubic centimeter. For comparison, the air you breathe contains about 30 billion atoms per cubic centimeter. This cloud is almost empty, yet it is still 300 times denser than the local bubble that surrounds it. Here is where it gets interesting. The cloud is moving relative to the solar system at about 16 m/s, but the solar system is also moving relative to the galaxy at around 140 m/s. When you combine these motions, you get something called the local interstellar wind, a flow of gas streaming through our solar system at roughly 16 m/s from the direction of the constellation Ophiuchus. This wind does not blow like air on Earth. Space is too empty for fluid dynamics to work the same way. Instead, individual atoms and ions flow past the solar system like rain falling through a moving car. Some particles enter our heliosphere, the protective bubble created by the solar wind. Most flow around the outside, deflected by magnetic fields and pressure from our sun. Scientists confirm the existence of the local interstellar cloud by measuring the absorption of light from distant stars. When starlight passes through gas, certain wavelengths get absorbed depending on what elements are present in the cloud. By analyzing these absorption patterns in the light from multiple stars, astronomers mapped out the cloud's location, temperature, density, and chemical composition. The cloud definitely exists. We definitely live inside it. The cloud is partially ionized, meaning some of its atoms have lost electrons and carry electric charges. This ionization happens because ultraviolet light from nearby stars strips electrons away from neutral atoms. The charged particles interact with magnetic fields, creating complex structures and flows that ordinary neutral gas cannot produce. What makes astronomers slightly nervous is the question of how long we have been inside this cloud. The best estimates suggest we entered the local interstellar cloud sometime between 44,000 and 150,000 years ago, depending on whose calculations you trust. That is extremely recent in cosmic terms. Before that, we occupied a different region of the local bubble with possibly different gas properties, different densities, different temperatures. The cloud is moving through the local bubble, and so are we, but not in the same direction or at the same speed. Eventually, within another 10,000 to 50,000 years, depending on which model you believe, we will exit the local interstellar cloud and enter a different region. Maybe another cloud, maybe empty space within the local bubble. The environment will change. The density of gas around the solar system will shift. The amount of interstellar material flowing into our heliosphere will increase or decrease. Some researchers suggest these changes could affect the Earth's climate over very long timescales. More interstellar gas entering the heliosphere might compress the protective bubble slightly, allowing more cosmic rays to reach Earth's atmosphere. Those cosmic rays could ionize atmospheric particles, potentially influencing cloud formation and climate patterns. The effects would be subtle, far too weak to cause an ice age or mass extinction, but possibly strong enough to show up in long-term climate records. The local interstellar cloud is part of a larger structure, a complex of multiple clouds, all moving through the local bubble in different directions. The clouds have names like the G cloud and the Ursa Major moving group. They interact with each other, merge, separate, and flow around obstacles created by stellar winds and magnetic fields. Our solar system is swimming through this cosmic ocean, and the water keeps changing. What lies ahead on our path through the galaxy? Different clouds, different densities, different unknowns waiting in the void. Wrapped around our solar system like a tilted crown sits a ring of death. Young, massive stars burn there, stars that will explode within the next few million years. This structure stretches 3,000 light-years across, tilted 20 b relative to the galactic plane. Astronomers call it Gould's Belt, and it surrounds us completely. The belt was discovered in the 1800s by Benjamin Gould, who noticed that the brightest stars in our night sky do not distribute evenly across the celestial sphere. Instead, they cluster along a great circle, tilted relative to the Milky Way's main band of light. That circle marks Gould's Belt, a ring of recent star formation containing thousands of hot, young stars destined to die violently. The belt includes some of the most famous star-forming regions visible from Earth. The Orion Nebula sits within it. So does the Scorpius-Centaurus Association, the same group of stars responsible for the supernovae that created the local bubble. The entire structure is filled with stellar nurseries, places where gas clouds collapse under their own gravity to form new stars. Here is what makes it unusual. Most star formation in the Milky Way happens in the galactic plane where gas and dust concentrate. But Gould's Belt tilts 20 bictors away from that plane, creating a ring structure that rises above and dips below the main stellar disk. Scientists still debate how this structure formed. The most popular theory suggests a supernova explosion or a collision with a gas cloud about 30 million years ago triggered a wave of star formation that expanded outward in a ring pattern, eventually creating the structure we observe today. The stars in Gould's Belt are young by cosmic standards. Most are less than 30 million years old. Some are still forming right now, wrapped in cocoons of dust and gas. These are O-type and B-type stars, the hottest and most massive stars in the galaxy. They burn blue-white, radiating enormous amounts of ultraviolet light. They consume their fuel so quickly that they will exhaust their nuclear cores within just a few million years, then detonate as supernovae. The belt is dangerous, not because it exists, but because it changes. Star formation continues. New massive stars light up inside the ring. Each one is a ticking time bomb with a fuse measured in millions of years. When they explode, they will feed new energy into the surrounding space, possibly expanding the local bubble further, potentially triggering new waves of star formation. Some of these stars have already died. We just have not seen the light from their explosions yet. A star 500 light years away could have detonated 400 years ago, and the light from that blast is still traveling toward us through space. We would not know until the wavefront arrived. Suddenly, a new point of light would appear in the night sky, bright enough to see during the daytime, lasting for weeks or months before fading. The nearest massive star in Gould's belt currently sits about 400 light-years away. That is close by galactic standards, close enough that a supernova would be visible as a spectacular object in our sky, but far enough that the radiation would not threaten Earth directly. The real danger comes from stars within a few dozen light-years. At that distance, gamma rays and X-rays from the explosion could impact Earth's atmosphere, potentially depleting the ozone layer and increasing surface radiation level. Astronomers continuously monitor the massive stars in our neighborhood, looking for signs of instability that might indicate an imminent explosion. Stars swell as they run out of fuel. They eject mass in powerful stellar winds. They flicker and dim in ways that suggest internal chaos. So far, no stars in Gould's belt show clear signs of exploding in the next few centuries, but predictions remain uncertain. Stars can surprise us. The belt also contains dozens of smaller star clusters and associations, groups of stars born from the same gas clouds at roughly the same time. These clusters drift through space together, gradually spreading apart over millions of years as individual stars follow slightly different orbits around the galaxy. Earth is not part of any cluster. Our sun formed elsewhere, probably 4.2 billion years ago, in a completely different region of the galaxy, then wandered here over time. But now we find ourselves inside Gould's belt, surrounded by stars that will explode long before our sun dies. We live in a ring of fire, and that fire has not finished burning. Your planet exists inside a bubble blown by the sun. This bubble protects you from the galaxy. Without it, interstellar radiation would slam into Earth at full intensity. Cosmic rays would bombard the atmosphere constantly, and life as you know it might never have evolved. This protective shield is called the heliosphere, and it has limit. The sun constantly spews charged particles into space. Protons, electrons, helium nuclei, all accelerated to speeds between 200 and 500 millivolts. This stream of particles is the solar wind, and it flows outward in all directions, filling the space around the sun with a hot, magnetized plasma. The solar wind does not stop at the edge of the planetary orbits. It keeps going, expanding outward until something stops it. That something is the interstellar medium. All the gas and dust floating between stars creates pressure pushing inward on our solar system from every direction, where the outward pressure of the solar wind equals the inward pressure of the interstellar medium. A boundary forms. This boundary, called the heliopause, marks the edge of the heliosphere and the beginning of true interstellar space. For decades, scientists predicted where this boundary should exist, based on theoretical models of how solar wind pressure decreases with distance and how interstellar pressure pushes back. The calculations suggested the heliopause should lie somewhere between 80 and 150 astronomical units from the Sun, though the exact distance remained uncertain because we did not know precisely how dense the surrounding interstellar medium was. Then Voyager 1 crossed it on August 25, 2012, at a distance of 21 astronomical units. Voyager 1 detected a sudden drop in solar wind particles, a sharp increase in galactic cosmic rays, and a change in the direction of the magnetic field. The spacecraft had crossed the heliopause into interstellar space. The measurements confirmed the boundary exists exactly where theory predicted. But here is what surprised scientists. The heliosphere is not round. Early models assumed the solar wind would create a spherical bubble, expanding equally in all directions. Reality is messy. Observations from multiple spacecraft, including the Interstellar Boundary Explorer mission, revealed that the heliosphere is asymmetric, possibly teardrop-shaped, or even more irregular. The shape depends on the direction the solar system moves through the interstellar medium and on local variations in gas density and magnetic field strength. The local interstellar cloud surrounding us pushes on the heliosphere unequal. In the direction we are moving, called the upstream direction, the heliosphere compresses slightly as our motion through the cloud creates a ram pressure effect. In the opposite direction, the downstream side, the heliosphere extends farther outward, where interstellar pressure is weaker. Some models suggest a tail might trail behind us, stretched out by our motion through the galaxy, though this remains debated. Inside the heliosphere, the solar wind shields us from most interstellar particles and galactic cosmic rays. These high-energy particles, accelerated by supernovae and other violent events across the galaxy, constantly bombard our region of space. Most get deflected or slowed by the magnetic fields embedded in the solar wind. Only a fraction penetrate all the way to Earth's orbit, and even fewer make it through Earth's own magnetic field to reach the atmosphere. But the shield is not perfect. The sun's activity varies on an 11-year cycle. During solar maximum, when the sun produces more solar wind and stronger magnetic fields, the heliosphere expands slightly and blocks more cosmic rays. During solar minimum, the heliosphere shrinks and weakens, allowing more cosmic rays to penetrate. Earth experiences measurable increases in cosmic ray flux during these quiet periods, and the heliosphere changes size depending on what cloud we pass through. When the solar system travels through denser regions of the interstellar medium, the increased external pressure compresses the heliosphere, moving the heliopause closer to the sun. In emptier regions, the heliosphere expands. Scientists estimate the heliopause could move inward by 20 or 30 astronomical units if we entered a sufficiently dense cloud, bringing interstellar space significantly closer to Earth. What happens if the heliosphere shrinks too much? More cosmic rays reach Earth. More interstellar gas flows into the inner solar system. The increased radiation could affect satellites, spacecraft, and potentially even atmospheric chemistry. Some researchers suggest major changes in the heliosphere's size might influence Earth's climate over millions of years, though the evidence remains weak. What is certain is this: the shield protecting you is not fixed. It breathes, it flexes, and its strength depends entirely on what we fly through in the galaxy outside. There is a line in space where our sun stops being the dominant force. Beyond this line, the galaxy takes over. Voyager 1 crossed that line on August 25th, 2012, becoming the first human-made object to enter true interstellar space. The crossing happened at exactly 12 to 21 astronomical units from Earth, roughly 11.3 billion miles away. The journey took Voyager 1 35 years. Launched in September 1977, the spacecraft flew past Jupiter, then Saturn, then headed toward the outer reaches of the solar system, carrying messages from humanity in case it ever encountered intelligent life. It carried no more planetary objectives. Its mission became purely to explore the boundary between the sun's domain and the galaxy beyond. For years before the crossing, Voyager 1's instruments detected changes. Cosmic ray levels gradually increased as the spacecraft moved farther from the sun and the protective shielding from solar wind weakened. The solar wind itself decreased in density and pressure. The spacecraft was approaching something, though scientists could not predict exactly when the boundary would arrive. Then, in June 2012, Voyager 1 wired a rapid 9% increase in cosmic ray flux over just 1 month. The increase continued through July and August. Something dramatic was happening. On August 25th, the spacecraft detected a sudden drop in solar wind particles. Within days, the count fell from about 25 particles per second to about 2 particles per second. Simultaneously, galactic cosmic rays increased sharply. The magnetic field direction shifted. Voyager 1 had crossed the heliopause. The sun's influence had ended. True interstellar space had begun. But here is what confused scientists at first. The magnetic field did not change as much as expected. Theory predicted that inside the heliosphere, the magnetic field would be dominated by the sun, carrying a specific orientation determined by solar activity. Outside the heliosphere, the magnetic field should shift to align with the local interstellar field coming from completely different directions. determined by galactic processes. The field direction did change, but subtly. This suggested the local interstellar magnetic field might be oriented similarly to the Sun's field in that region of space. A coincidence nobody anticipated, or perhaps the boundary region between the heliosphere and interstellar space is more complicated than simple models suggested, with overlapping fields and transition zones rather than a sharp divide. Voyager 2 crossed the heliopause 6 years later in November 2018 at a distance of 119 astronomical units. The crossing confirmed what Voyager 1 discovered, but added new puzzles. The two spacecraft crossed at different distances, proving the heliopause's boundary is not a perfect sphere, wrinkles and shifts, responding to changes in solar wind pressure and variations in the surrounding interstellar medium. Both spacecraft continue transmitting data even now, though their power sources are fading. The radioisotope thermoelectric generators that provide electricity are decaying, producing less power each year. By the late 2025s or early 2030s, both Voyagers will likely stop functioning, falling silent as they drift deeper into interstellar space, carrying their golden records with recordings of Earth sounds, music, and greetings in dozens of languages. Beyond the heliopause, the universe is different. Radiation levels spike. The temperature of surrounding plasma increases from about 50,000 degrees inside the heliosphere to much hotter values outside. The density of neutral atoms changes. The Sun becomes just another star, no longer the overwhelming gravitational and electromagnetic presence it was closer in. But even at 121 astronomical units, the Sun's gravity still dominates. Planets orbit closer than 50 astronomical units. The Kuiper belt extends to perhaps 100 astronomical units, but gravity reaches much farther. The question is not whether the Sun's gravity extends beyond the heliopause, but rather where that gravity stops being strong enough to hold objects in orbit. That boundary, where objects become more loyal to the galaxy than to the Sun, lies far beyond where Voyager 1 crossed into interstellar space. That boundary sits at the edge of the Oort Cloud, and what waits there makes the heliopause's crossing look like stepping across a doorway. Out there at the true edge, the Sun's power finally dies completely. Imagine a sphere of frozen objects surrounding our solar system. The sphere extends from 2,000 astronomical units out to 200,000 astronomical units from the Sun. That is roughly 3 light-years in diameter, reaching nearly halfway to the nearest star. Inside this sphere, trillions upon trillions of icy chunks orbit in darkness, most smaller than a city, some as large as mountains. This is the Oort Cloud, and we have never directly observed a single object inside it. The cloud's existence is inferred, not confirmed. We see comets entering the inner solar system from random directions, not from the ecliptic plane where planets orbit, not from the Kuiper belt's flattened disk. These comets arrive from above, below, and all sides equally, suggesting they come from a spherical reservoir surrounding us. The math works. The orbital mechanics check out. The cloud almost certainly exists, but we cannot see it directly because the objects are too small, too dark, and too far away to reflect enough sunlight for our telescopes to detect. Astronomer Jan Oort proposed the cloud in 1950 after studying long-period comet orbits. He noticed these comets had orbital periods of thousands or millions of years and arrived from seemingly random directions. Something had to be nudging them out of distant orbits and sending them sunward. Oort calculated that a spherical cloud of icy debris at enormous distances could explain the observations. The idea stuck. The cloud was named after him. Here is what lives in the Oort Cloud. Leftover debris from the solar system's formation 4.6 billion years ago, when planets formed from the rotating disk of gas and dust around the young sun. Not everything got incorporated into planets. Small chunks of rock and ice were flung outward by gravitational interactions with Jupiter, Saturn, Uranus, and Neptune. Some of these chunks escaped the solar system entirely. Others did not have quite enough speed to escape, but reached such distant orbits that they barely remained bound to the sun. Over billions of years, these objects spread out into a roughly spherical shell. Gravitational tugs from passing stars, the tidal force from the Milky Way, and random encounters gradually circularized their orbits and distributed them evenly around the solar system. The result is the Oort cloud we theorize exists today. The cloud is divided into two regions. The inner, Oort cloud, also called the Hills cloud, after scientist Jack Hills, who proposed it in 1981, extends from about 2,000 to 20,000 astronomical units. This region might be donut-shaped, concentrated around the ecliptic plane. It is denser than the outer cloud, possibly containing tens or hundreds of times more objects, but still too sparse for any two comets to be close neighbors. Each object drifts alone in the dark, separated from its nearest companion by distances measured in billions of miles. The outer Oort cloud extends from 20,000 to 200,000 astronomical units. This region is definitely spherical, surrounding the entire solar system equally in all directions. The objects here orbit so slowly that a single trip around the sun takes millions of years. Some comets in the outer cloud have never completed even one orbit since they arrived there shortly after the solar system formed. Estimates for the total number of objects in the Oort cloud vary wildly. Conservative estimates suggest several trillion objects larger than half a mile across. More optimistic estimates reach tens of trillions. The total mass probably equals a few times the mass of Earth, maybe 5 to 10 Earth masses, if you include everything down to tiny pebbles, though this remains highly uncertain. These objects are they have not been heated by the sun significantly since the solar system's formation. They contain ice from the original molecular cloud that collapsed to form our solar system. Studying them would provide direct evidence of what the early solar system looked like, but we cannot reach the fastest spacecraft ever built. New Horizons travels at about 36,000 km/h relative to Earth. At that speed, reaching the inner edge of the Oort cloud would take roughly 500 years. Reaching the outer edge would take 30,000 years. So the Oort cloud remains a ghost. We know it is probably there. We see its effects when comets fall inward toward the sun, but we cannot touch it, cannot photograph it, cannot confirm its structure directly. It sits at the edge of the sun's gravitational dominance, the last objects still bound to our star before the galaxy takes over completely, and something out there is shaking it. Something is disturbing those distant orbits, sending comets falling toward Earth. What force can reach across light years of space and shake a trillion frozen chunks of ice? The answer lies in the galaxy itself. Between the outer planets and the spherical Oort cloud sits a structure scientists predicted in 1981, but still cannot directly observe, a donut-shaped swarm of icy objects packed far more densely than the outer cloud. This is the Hills cloud, named after astronomer Jack Hills, and it might explain why comets keep falling toward Earth, even after billions of years should have emptied the outer Oort cloud. The problem is simple. Objects in the outer Oort cloud orbit so far from the sun that their gravitational binding is weak. A passing star, even one coming within a few light years, exerts enough tidal force to strip comets away or send them into different orbits. Over 4.6 billion years, the outer cloud should have been depleted significantly. Random encounters with stars should have scattered most of its contents across the galaxy. Yet, long-period comets keep arriving. The supply seems nearly constant. Hills proposed a solution. Maybe a denser reservoir sits closer to the sun, inside the outer cloud sphere. This inner region would be more tightly bound by solar gravity, less vulnerable to disruption by passing stars or galactic tides. Objects in the Hills cloud could survive for billions of years, occasionally getting knocked into the outer cloud or directly into the inner solar system by gravitational perturbations. Computer simulations confirmed the Hills cloud should exist. When researchers modeled the formation of the Oort cloud, tracking how small icy objects got ejected from the inner solar system by planetary encounters, they found that objects did not just fly directly outward into a spherical shell. Many settled into intermediate orbits, forming a thick donut-shaped structure aligned roughly with the ecliptic plane. This inner cloud naturally emerged from the physics of planetary migration and gravitational scattering. The Hills cloud probably extends from about 2,000 astronomical units to 20,000 astronomical units from the Sun. Its thickness might be several thousand astronomical units above and below the ecliptic plane. The density should be tens or even hundreds of times greater than the outer Oort cloud, meaning the majority of cometary nuclei in the entire Oort cloud complex actually reside in the Hills cloud rather than the better-known outer sphere. Here is where things get strange. A recent paper published in early 2025 suggested the Hills cloud might not be a simple donut. The researchers ran more detailed simulations and found that gravitational interactions with the planets, especially during the early solar system when planets were still migrating, could twist the inner cloud into a spiral structure. Instead of a uniform ring, the Hills cloud might look more like a loosely wound spiral, with density variations depending on angle and distance from the Sun. This spiral structure would explain some anomalies in long-period comet statistics. Comets do not arrive perfectly uniformly from all directions, as a purely spherical outer cloud would suggest. There are subtle preferences, slight anisotropies that hint at an underlying structure. If the Hills cloud has spiral features, those features could bias the directions from which comets eventually fall toward the Sun. The Hills cloud matters because it acts as a reservoir, constantly replenishing the outer Oort cloud. As objects in the outer cloud get stripped away by passing stars or scattered by galactic tides, the Hills cloud feeds new comets outward to replace them. Without this inner reservoir, the Oort cloud would have dispersed long ago, and long-period comets would have stopped arriving in the inner solar system billions of years before Earth developed life. But the Hills cloud also makes our solar system more vulnerable to certain kinds of disturbance. A star passing within a few light years might not disrupt the Hills cloud significantly, but a star coming within 10,000 to 50,000 astronomical units, passing through or very near the inner cloud, could scatter huge numbers of comets simultaneously. Such an encounter could trigger a comet shower, sending hundreds or thousands of comets falling toward the inner solar system over a period of a few million years. Has this happened? Possibly. Some researchers suggested that periodic comet showers might correlate with extinction events on Earth, triggered by stars passing through the Hills cloud and sending swarms of comets inward. Multiple impacts over a short geological time span could have catastrophic effects on Earth's climate and biosphere. The evidence remains controversial, but the physics is sound. The Hills cloud, if it exists as predicted, makes our solar system vulnerable to stellar close encounters in a way that a purely spherical outer cloud would not. And nobody can confirm any of this directly, because the Hills cloud sits far beyond where we can send spacecraft, far beyond where our telescopes can detect individual objects. It remains theoretical, predicted by models and simulations, but never actually observed. It is a fortress we believe protects the outer Oort cloud, but cannot see, and something is shaking that fortress. Something reaches across thousands of astronomical units and disturbs those frozen orbits. The galaxy itself is pulling on those comets. The Milky Way is trying to tear apart the Oort cloud, not violently, not quickly, but continuously, relentlessly. The galaxy's gravity squeezes and stretches the outer solar system, distorting the orbits of comets at the edge of the Sun's influence. This force is called the galactic tide, and it is the main reason long-period comets fall toward Earth. Think about how the Moon creates ocean tides. On Earth, the Moon pulls harder on the side of Earth closest to it than on the far side, because gravity weakens with distance. This difference in gravitational pull stretches Earth slightly, creating a bulge of water facing the Moon and another bulge on the opposite side. The tides rise and fall as Earth rotates through these bulges. The same principle operates on the Oort cloud, but the forces come from the Milky Way's mass distribution. The galactic disk contains most of the galaxy's visible matter, stars and gas packed into a flat structure. This mass pulls on the solar system, but it pulls harder on the side of the Oort cloud facing toward the galactic disk than on the side facing away. The difference in pull creates a tidal force that stretches the cloud, but the galactic tide is more complicated than a simple tidal bulge. The Milky Way's mass is not concentrated at a single point, like the Moon is for Earth. Matter spreads throughout the galactic disk, and the solar system orbits around the galactic center, creating additional forces. Astronomers break the galactic tide into two main components. The radial component points toward or away from the galactic center. This force comes from the fact that the solar system orbits in a curved path around the galaxy. Objects in the Oort cloud on the side toward the galactic center experience slightly stronger gravity pulling them inward than objects on the far side. This difference creates a squeezing effect along the line pointing toward the galactic center. The vertical component points perpendicular to the galactic plane. This force results from all the mass in the galactic disk pulling objects toward the plane. Comets in the Oort cloud above the galactic plane feel a downward pull toward the disk. Comets below the plane feel an upward pull. This component squeezes the Oort cloud along the axis perpendicular to the galactic disk and stretches it along the other two axes. The Milky Way's dark matter halo is enormous. Computer simulations suggest it extends at least 600,000 light-years from the galactic center, possibly farther. The total mass might be 10 times the mass of all visible stars, gas, and dust combined. This halo is not empty space. It is filled with dark matter particles, whatever those particles are, concentrated enough to hold the galaxy together, but still diffuse enough that the density is extremely low. Here is where it affects the solar system. The dark matter halo contributes to the galactic tide, acting on the Oort cloud. When scientists calculate the tidal forces squeezing and stretching the outer solar system, they must include two components. One component comes from the visible matter in the galactic disk, all the stars and gas we can directly observe. The other component comes from the dark matter halo. The dark matter contribution adds about 15% to the total galactic tide. That might not sound like much, but at the distances of the Oort cloud, where forces are extremely weak, 15% matters. It means comets get perturbed slightly faster than they would if only visible matter existed. The timescale for orbital changes shortens. The rate at which comets fall into the inner solar system increases. Some researchers have suggested we might be able to detect dark matter directly in the solar system if its density is high enough locally. The idea is that dark matter particles, though they do not interact with light, might interact weakly with normal matter through other forces. Rare collisions between dark matter particles and atomic nuclei in detectors on Earth could produce measurable signals. So far, no dark matter particle has been definitively detected, despite decades of searching with increasingly sensitive experiments. The null results place strong limits on how dark matter can interact with normal matter. Either dark matter is even more ghostly than expected, interacting through forces so weak we cannot yet measure them, or dark matter is composed of something more exotic than theoretical models currently predict. But dark matter definitely exists. The gravitational evidence is overwhelming. Galaxies would fly apart without it. Galaxy clusters would disperse. The large-scale structure of the universe, the web of galaxies and voids we observe on the largest scales, would not form correctly in computer simulations without dark matter providing gravitational scaffolding. Something invisible holds the universe together, and we call it dark matter, even though we do not know what it is made of. For the Oort cloud, what matters is that this invisible halo contributes to the forces pulling on distant comets. The dark matter cannot be ignored when calculating orbital dynamics at the solar system's edge. It changes how quickly the galactic tide disrupts orbits. It affects where the tidal truncation radius sits. It helps determine the boundary between what remains part of the solar system and what escapes into the galaxy. Recent studies suggested something even stranger. The dark matter halo might not be small. It might contain substructure, smaller clumps, and streams of dark matter moving through the galaxy. If one of these clumps passed through the Oort cloud, it could gravitationally scatter comets far more effectively than the smooth halo does. The encounter might trigger a comet storm, sending thousands of comets plunging toward the inner solar system within a geologically short time span. Has this happened? We do not know. The evidence for dark matter substructure remains uncertain, and detecting such an event in Earth's geological record would be extremely difficult. But the possibility exists. The dark matter halo surrounding us is not just a uniform background. It might contain structures, features, possibly even caustics where dark matter density spikes sharply. And if those features pass through our neighborhood, they could shake the Oort cloud in ways we have not experienced for billions of years. Hidden in the dark matter halo surrounding the Milky Way are sharp boundaries where density spikes by orders of magnitude. These boundaries are called caustics, and they form naturally when cold dark matter falls into a galaxy. The caustics exist as surfaces in three-dimensional space, places where dark matter from multiple directions flows together and piles up. If a caustic passes through the solar system, it could scatter comets in the Oort cloud far more violently than the smooth background halo does. Here is how caustics form. When the Milky Way first assembled billions of years ago, dark matter fell inward toward the center from all directions. This infall was not smooth. Dark matter came in streams and flows converging from different angles. Where these flows intersected, dark matter density increased sharply. The flows could not pass through each other because dark matter is collisionless. Instead, they piled up at the intersection points, creating thin sheets of enhanced density. These sheets are caustic. The word comes from optics, where caustics describe patterns of focused light, like the bright lines you see on the bottom of a swimming pool when sunlight refracts through rippling water. In the dark matter context, caustics are regions where dark matter focuses gravitation. The density can be 10, 100, even 1,000 times higher inside a caustic compared to the surrounding smooth halo. The caustics form rings in the galactic plane. The first caustic ring sits closest to the galactic center, maybe 10,000 light-years out. Subsequent rings space farther apart, with the fifth ring possibly sitting around 27,000 light-years from the center, close to the sun's current location. Some research suggested we might actually be inside the fifth caustic ring right now, orbiting through a region of enhanced dark matter density. If this is true, it has implications. The local dark matter density would be higher than average, potentially making dark matter detectors on Earth more likely to see signals. The gravitational effects on the Oort cloud would be stronger, and if the solar system's orbit takes us in and out of the caustic ring over millions of years, the strength of dark matter perturbations on the Oort cloud would vary with time. But caustics do more than just sit there. They move. The rings expand outward over cosmic timescales as the galaxy evolves. A caustic ring moving through the solar system would create a temporary enhancement in dark matter density, lasting perhaps a few 100,000 years as the ring swept past. During that time, the extra gravitational pull from the caustic could disturb Oort cloud comets more strongly than normal. Scientists calculated what would happen if a caustic passed through the Oort cloud. The enhanced dark matter density would gravitationally tug on comets, changing their orbits. The effect would not be dramatic for most comets, because even caustic dark matter is diffused by everyday standards. But at the edge of the Oort cloud, where gravitational binding is already weak, the extra perturbation might be enough to knock some comets into orbits that bring them toward the inner solar system. The probability of a noticeable effect is low, maybe 0.003% chance of significantly affecting comet flux during a caustic passage, but not zero. If caustics pass through the solar system every few tens of millions of years, there is a chance that at least once or twice in Earth's history, a caustic encounter boosted the rate of cometary impacts. Whether this actually happened, and whether we could detect evidence of it in the geological record, remains an open question. The existence of caustics themselves remains somewhat controversial. The prediction comes from simulations of cold dark matter halos, and some evidence from stellar motion in the Milky Way suggests caustic-like structures might exist. But dark matter detection experiments have not yet confirmed the presence of caustics directly. If dark matter turns out to be something other than cold collisionless particles, caustics might not form at all. What makes caustics particularly interesting is their sharpness. Unlike the smooth dark matter halo that changes density gradually over thousands of light years, a caustic is a surface just a few light years thick, where density jumps suddenly. Crossing a caustic would be like crossing a boundary in space where gravitational conditions abruptly change. For the Oort cloud, this could mean entering a region where dark matter tides suddenly strengthen, lasting for the time it takes the solar system to traverse the caustic sheet. No one knows if we are approaching a caustic now, moving away from one, or nowhere near any caustic structure. The uncertainties in both the solar system's orbit around the galaxy and the locations of hypothetical caustic rings are too large to make precise predictions. We might pass through a caustic tomorrow, or we might not encounter one for 100 million years. The dark matter halo keeps its secrets. It pulls on us constantly, invisibly, and we cannot see where its density peaks hide in the darkness. Above and below the galactic plane, out beyond the thin disk of stars where most visible matter concentrates, space fills with gas heated to temperatures that would vaporize any solid object instantly. This is the galactic halo gas, a diffuse plasma spread across hundreds of thousands of light years, glowing faintly in X-rays. The temperature reaches 1 million degrees Kelvin or more, hot enough to strip electrons from atoms and create a soup of charged particles that interacts with magnetic fields in complex ways. This hot halo is not the same as the dark matter halo. The dark matter halo is invisible and spreads even farther into space. The hot gas halo is normal matter, mostly hydrogen and helium, with traces of heavier elements, but it is so hot and diffuse that it emits very little visible light. Only X-ray telescopes can detect it by observing the high-energy photons produced when electrons in the hot plasma decelerate or transition between energy levels in ionized atoms. The mass of the hot halo is enormous. This gas represents much of the galaxy's missing baryonic matter, the normal matter that theoretical models predicted should exist, but that astronomers could not find for decades. The problem was, they were looking in the wrong wavelength. The gas does not emit visible light because it is too hot. You need X-ray vision to see it. Where does the heat come from? Two main sources. Supernova explosions in the galactic disk inject enormous amounts of energy into surrounding gas. The shock waves from these explosions heat gas to millions of degrees and blast it upward out of the disk into the halo. This creates what astronomers call a galactic fountain. Hot gas rises, cools as it travels, eventually falls back down toward the disk under gravity, where it gets heated and blasted upward again. The cycle repeats continuously. The second source is gravitational energy. As the Milky Way formed, gas fell inward toward the center, converting gravitational potential energy into kinetic energy and heat. This accretion heating can raise gas temperatures to millions of degrees. Even now, the galaxy continues accreting gas from the intergalactic medium, and this fresh gas gets heated as it falls into the potential well of the galaxy's gravity. The hot halo is not uniform. It has structure, temperature, and density vary depending on location. Near the galactic plane, where supernovae explode most frequently, the gas is hotter and more turbulent. Farther above and below the plane, the gas cools slightly and becomes smooth, but everywhere, the temperature stays above a few 100,000 degrees, keeping the gas ionized and making it invisible to normal optical telescopes. Recent X-ray observations revealed giant bubbles in the hot halo, extending thousands of light years above and below the galactic center. These bubbles, detected by the Heliosphere telescope, appear to be shock-heated regions created by past activity in the Milky Way's central black hole. Millions of years ago, perhaps 10 million years ago, the central black hole might have been more active, accreting matter and blasting jets of energy perpendicular to the galactic plane. Those jets inflated enormous bubbles in the surrounding halo gas, and we still see the remnants today. The hot halo interacts with everything passing through it. High-velocity clouds, chunks of cold gas falling toward the galaxy, plow through the hot halo and create shock fronts, stellar streams. trails of stars ripped from disrupted satellite galaxies move through the halo and experience drag from the diffuse gas. Even the solar system interacts with the halo, though we are too close to the galactic plane to feel significant effects from the hottest regions above and below us. For structures far above or below the galactic plane, the hot halo dominates the environment. Globular clusters, ancient spheres of stars orbiting through the halo, swim through this million-degree plasma continuously. Dwarf galaxies on the outskirts of the Milky Way experience ram pressure as they move through the halo gas, stripping away their own gas and leaving trails behind them like comets. The halo gas also contains metals, elements heavier than helium. These metals were produced inside stars through nuclear fusion and then ejected into space when those stars exploded as supernovae or lost their outer layers in stellar winds. The presence of metals in the hot halo proves that material from the galactic disk gets transported outward and upward into the halo, mixing material enriched by stellar processes throughout the galaxy's vertical extent. Scientists estimate the halo gas will remain hot for billions of years. Cooling processes exist but operate slowly at such low densities. The gas radiates energy as X-rays, but the cooling timescale is longer than the age of the universe at the densities found in most of the halo. Only in the densest regions near the galactic plane does the gas cool enough to fall back and replenish the disk. This hot halo is part of the answer to what lies above and below the solar system. Go far enough up or down, and you leave the comfortable realm of stars and enter a zone dominated by invisible dark matter and hot glowing plasma. A realm where temperatures soar, but densities plunge so low that you could travel for light years without encountering enough atoms to fill a thimble. A realm where the rules change and the galaxy's true structure reveals itself. In December 2020, astronomers using the Rosetta X-ray telescope discovered something terrifying. Two enormous bubbles extend 14,000 light-years above and below the galactic center. 14,000 light-years, that distance is half the radius of the visible Milky Way disk. These bubbles glow with X-ray light invisible to human eyes, marking regions where gas was shocked and heated to temperatures exceeding 2 million. The bubbles are nearly symmetrical, one above the galactic plane and one below. Their edges are sharp, tracing collisionless shocks, where hot gas slams into cooler surrounding material. The southern bubble includes a structure astronomers have puzzled over for decades, called the North Polar Spur, a massive arc of radio and X-ray emission visible from Earth's northern hemisphere. Nobody realized until Rosetta that the North Polar Spur is just one edge of a galaxy-scale bubble. What created these monsters? Two possibilities exist: either a burst of star formation in the galactic center or activity from the supermassive black hole. Both processes can inject enough energy to inflate bubbles this large. Scientists estimate the total energy required equals about 100,000 supernovae exploding in a relatively short time, or 1 million solar masses of material falling into the central black hole and converting a fraction of that mass into radiation and kinetic energy. The timing appears to be millions of years ago, possibly 10 to 20 million years back. The bubbles are not expanding rapidly now. They appear to be in a late stage of evolution, coasting outwards slowly as they age. The shock fronts at their edges have weakened compared to what they must have been initially, but the structure persists, visible across thousands of light years, marking one of the most violent events in recent Milky Way history. The bubbles interact with everything they encounter. High-velocity clouds that stray too close get accelerated or disrupted by the shock fronts. Magnetic fields in the galactic halo get compressed and amplified along the bubble walls. Cosmic rays, high-energy particles accelerated by the shocks, stream along the bubble edges and into the surrounding space. Some of these cosmic rays might eventually reach Earth. Scientists compared the X-ray bubbles to structures seen in other wavelengths. Gamma-ray telescopes had previously detected similar bubbles called the Fermi bubbles, named after the Fermi Gamma-ray Space Telescope. The Fermi bubbles align almost perfectly with the Rosetta X-ray bubbles, confirming they are the same structures seen in different types of light. Radio telescopes also detect emission from the bubble regions, revealing the presence of magnetic fields and relativistic particles. What makes the discovery significant is the scale. These are not local features, these are galaxy-wide structures that demonstrate the Milky Way's central region can produce outbursts powerful enough to affect the entire halo. If you lived on a planet in a star cluster located above the galactic plane inside one of these bubbles, your sky would be bombarded with radiation from the shock-heated gas. Life would face challenges Earth never experienced. The bubbles also reveal information about the galactic center's history. The Milky Way's central black hole is quiet now. It accretes material slowly, producing relatively little radiation compared to active galactic nuclei in other galaxies. But the bubbles prove our black hole was not always dormant. At some point in the past 10 million years, something fed the beast. A gas cloud fell in, or stars ventured too close and got torn apart, or perhaps a smaller galaxy merged with the Milky Way's core. Whatever happened unleashed enough energy to blast gas 10,000 light-years outward from the plane. The violence was extraordinary. The energy was staggering, and we see the evidence still glowing above and below us, marking the spot where our galaxy's heart exploded. The bubbles will fade eventually as the gas cools and disperses, but for now they remain giant scars in the halo marking ancient trauma. For 70 years, astronomers stared at a massive arc of radio and X-ray emissions stretching across the northern sky and argued about what it was. Some said it was a nearby supernova remnant, maybe a few hundred light-years away. Others claimed it was a distant galactic structure, thousands of light-years from Earth. Nobody could agree. The feature was called the North Polar Spur, and it dominated the radio sky above the galactic plane. The spur extends more than 100 rays across the sky when viewed from Earth. That angular size could mean a small object nearby or a massive structure far away. Distance measurements were impossible because the spur does not contain stars or other objects with measurable parallax. It is just gas glowing in radio waves and X-rays, with no clear indicators of how far away it sits. Some researchers favored the local supernova explanation. They calculated that a star exploding about 30,000 to 100,000 years ago, at a distance of a few hundred light-years, could create a shock wave expanding outward. By now, that shock wave would have grown large enough to appear as an arc spanning a huge chunk of sky. The X-ray emission would come from the shock-heated gas behind the expanding blast wave. Others pointed out problems with the local scenario. The energy required seemed too high for a single nearby supernova. The structure appeared too organized, too smooth, and the spur's orientation aligned suspiciously well with the galactic plane, rather than pointing randomly as a local supernova remnant should. These scientists argued the North Polar Spur must be part of a larger galactic structure, possibly associated with the Milky Way's central activity or with large-scale features in the halo. The Rosetta telescope settled the debate into the full-sky X-ray map revealed that the North Polar Spur is the southern edge of a massive bubble extending 14,000 light-years above the galactic center. The spur is not a separate object at all. It is part of the Rosetta bubbles described in the previous chapter. The mystery was solved by seeing the bigger picture. What looked like a local feature turned out to be a distant galaxy-scale structure. The confusion arose because the southern edge of the northern bubble happens to point roughly toward Earth. When you look north from Earth's position slightly above the galactic plane, you see the edge-on view of the bubble's shock front. That edge appears as the North Polar Spur. The rest of the bubble extends away from us, harder to see because we view it face-on rather than edge-on. The discovery resolved decades of arguments. The North Polar Spur is definitely associated with the galactic center's activity millions of years ago. The distance is roughly 25,000 light-years to the bubble's origin point, near the galactic center, though the spur itself is closer because it represents the near edge of the expanding structure. The energy source was either rapid star formation or black hole activity, both of which can produce enough power to inflate bubbles of this magnitude. But the story has a twist. The southern hemisphere has a similar structure, called the South Polar Spur. Though it is less prominent when viewed from Earth's northern hemisphere, this southern counterpart is part of the Rosetta bubble, extending below the galactic plane. Together, the two spurs mark the edges of the giant bipolar outflow from the Milky Way's core. The resolution of the North Polar Spur mystery demonstrates how difficult it is to determine distances to diffuse structures in space. Without clear distance indicators like stellar parallax or standard candles, astronomers must rely on morphology, energy requirements, and associations with other structures. Sometimes the answer only becomes clear when a better telescope reveals the full context. For Earth, the North Polar Spur's true nature means we are not inside a nearby supernova remnant, as some feared. We are simply viewing the edge of a much larger structure from our vantage point in the galaxy. The radiation from the spur is diluted by distance, posing no threat, but the structure reminds us that our galaxy's center can erupt violently, sending shocks and radiation thousands of light years outward. We live in a dynamic galaxy. The calm we experience now is not guaranteed to last forever. Wrapped around the Milky Way, like two donuts stacked above and below the galactic plane, are invisible magnetic field structures. These fields follow the rotation of the galaxy, creating toroidal patterns where field lines circle the galactic center in closed loops. The fields in the northern toroid point in one direction, the fields in the southern toroid point the opposite way. This asymmetry tells us something fundamental about how galaxies generate magnetic fields. Magnetic fields are generated by moving charged particles. In galaxies, the combination of rotation and convective motions in ionized gas creates a dynamo effect, similar to how Earth's liquid iron core generates our planet's magnetic field. The galactic dynamo operates on a much larger scale, spanning thousands of light years, but the basic principle remains the same. Moving plasma twists magnetic field lines, amplifying them over time until the field reaches an equilibrium strength. The toroidal halo fields sit above and below the galactic disk, extending perhaps 1 to 2,000 light-years in each direction. They exist separately from the magnetic fields in the disk itself, though the two components must connect somehow. The exact connection points and transition zones remain poorly understood, because mapping three-dimensional magnetic field structures from our position inside the galaxy is extraordinarily difficult. Scientists infer the halo field's existence from multiple observations. Polarized radio emission from distant background sources gets rotated as the radio waves pass through magnetized plasma in our galaxy. This rotation, called Faraday rotation, provides information about the strength and direction of magnetic fields along the line of sight. By measuring Faraday rotation toward thousands of background sources in different directions, astronomers can reconstruct a galaxy's magnetic field structure. The data showed a clear pattern, looking north from the galactic plane toward the North Galactic Pole. The Faraday rotation indicated magnetic fields pointing in one direction azimuthally around the galaxy. Looking south, the rotation indicated fields pointing the opposite azimuthal direction. This north-south asymmetry is a signature of toroidal fields with opposite orientations in each hemisphere. The field strength in the halo is weaker than in the disk. Where disk fields might reach 5 to 10 microgauss, halo fields measure perhaps 1 to 3 microgauss. A microgauss is 1/1,000,000th of a gauss, and Earth's magnetic field at the surface is about half a gauss. So galactic fields are extremely weak by everyday standards. But integrated over thousands of light years, these weak fields can have significant effects on charged particles and cosmic rays. The toroidal fields trap cosmic rays, high-energy particles accelerated by supernovae and other violent events. Charged particles cannot easily cross magnetic field lines. They spiral around field lines, remaining trapped in the halo for extended periods before eventually escaping into intergalactic space. This confinement increases the time cosmic rays spend in the galaxy, raising their density and increasing the probability they will eventually collide with gas or reach Earth. Recent models suggested the toroidal halo fields might extend farther than previously thought. Instead of stopping at 1 or 2,000 light-years above and below the plane, They might reach 10,000 light-years or more, filling much of the volume where the Eorosita bubbles exist. The magnetic fields would interact with the bubble shocks, getting compressed and amplified along the bubble walls. The existence of these ordered magnetic field structures on galaxy-wide scales surprised theorists when first discovered. Random turbulent motions in the interstellar medium should tangle magnetic fields into chaotic knots with no large-scale organization. But observations clearly show coherent structures spanning thousands of light-years. The galactic dynamo must be more efficient at organizing fields than simple turbulence models predicted. For objects in the galactic halo, these magnetic fields matter. Cosmic rays get channeled along field lines. Charged particles experience forces perpendicular to their motion, causing them to drift azimuthally around the galaxy. Even neutral gas can feel magnetic effects if it is partially ionized, with magnetic pressure and tension affecting its motion. And the fields are not static. They evolve as the galaxy rotates and as new dynamo activity generates fresh fields. Simulations suggest that toroidal structures might flip periodically over billions of years, with the northern field direction becoming the southern direction and vice versa. We might be observing the galaxy during one particular phase of a much longer magnetic cycle. The invisible magnetic donuts above and below us are part of the galactic machinery that shapes the halo environment. They guide particles, trap energy, and connect the disk to the halo in ways gravity alone cannot explain. You cannot see them, you cannot feel them, but they exist, wrapping the galaxy in electromagnetic architecture. Scattered throughout the space above and below the galactic plane are ancient spheres of stars called globular clusters. Each cluster contains hundreds of thousands to millions of stars packed into a ball, just tens of light years across. They orbit through the galactic halo on paths that take them far above and below the disk, returning to cross the plane every few 100 million years. Some clusters orbit clockwise around the galaxy. Others orbit counterclockwise, moving backward relative to the disk's rotation. These are among the oldest objects in the Milky Way. Globular clusters formed more than 10 billion years ago in the early universe, when the Milky Way was still assembling. The stars inside them contain very few heavy elements compared to the Sun because they formed before generations of supernovae had enriched the galaxy with metals. These are population 2 stars, ancient relics from the galaxy's youth, still burning slowly in the halo. About 50 globular clusters orbit the Milky Way. Most sit within 100,000 light-years of the galactic center, but a few venture much farther. The most distant known cluster orbits more than 200,000 light-years out, well beyond the visible galactic disk, out in the dark matter halo, where only gravity connects it to the galaxy. At that distance, the cluster's orbital period might be several billion years. The clusters do not orbit in the galactic plane. Their orbits tilt at random angles, crossing through the plane twice per orbit, but spending most of their time above or below it. This distribution is completely different from disk stars, which orbit nearly in the plane itself. The globular clusters belong to the halo population, objects that formed before the disk settled into its current flattened structure. About 40% of the Milky Way's globular clusters orbit retrograde, meaning they move opposite to the direction the galactic disk rotates. This backward motion is unusual. Disk stars all orbit in the same direction, prograde, because they formed from a rotating cloud of gas that collapsed into a disk. Retrograde orbits suggest a different origin. Many of these backward-moving clusters probably formed in smaller galaxies that the Milky Way captured and destroyed billions of years ago. The clusters survived as the galaxies that hosted them were torn apart by tidal force. Globular cluster orbits are not simple ellipses like planetary orbits. The galaxy's gravitational field is more complex than a point mass, with contributions from the disk, bulge, and dark matter halo, all pulling in different directions depending on location. Cluster orbits precess and wobble, sometimes dramatically. A cluster might follow a rosette pattern, looping around the galaxy along a path that never quite repeats exactly. These clusters pass through different environments as they orbit. When they cross the galactic plane, they plunge through denser regions filled with gas, dust, and stars. Interactions with giant molecular clouds can gravitationally disturb clusters, stripping away their outermost stars and gradually eroding them over billions of years. Some clusters have tidal tails, streams of stars stretched along their orbits, marking where the galaxy's gravity pulled stars away. In the halo, far above or below the plane, clusters experience a different environment. The density drops dramatically, stars are scarce, gas is hot and diffuse. The clusters swim through the million-degree halo plasma, moving at hundreds of miles per second, experiencing ram pressure as they push through the thin gas. The pressure is weak, but not zero. Over billions of years, even weak forces can shape cluster evolution. Scientists study globular clusters to learn about the early Milky Way. The clusters preserve information about the galaxy's initial conditions, locked in the chemistry and motions of their ancient star. By measuring cluster ages, compositions, and orbits, astronomers reconstruct the galaxy's assembly history. Which clusters formed in the Milky Way originally? Which came from accreted satellite galaxies? The answers help build a timeline of galactic evolution. Some clusters are dying. They lose stars continuously through a process called evaporation. Random gravitational encounters between stars inside the cluster occasionally give one star enough energy to escape. That star drifts away, reducing the cluster's total mass slightly. Over billions of years, this process can completely disintegrate a cluster, spreading its stars across the halo as a diffuse stellar stream. The clusters we see today are survivors. Many more clusters probably existed in the early Milky Way, but have since dissolved. The survivors are either massive enough or orbit far enough from the galactic center that tidal forces have not yet destroyed them. They will continue orbiting for billions of years more, ancient monuments to the galaxy's violent youth, floating in the halo above and below us. Painted across the galactic halo like cosmic spaghetti are long, thin trails of stars. These stellar streams mark the death sites of dwarf galaxies and globular clusters that venture too close to the Milky Way. Tidal forces stretch them apart, pulling stars from the leading and trailing edges of the doomed objects, leaving rivers of stars flowing around the galaxy in paths that trace their fatal orbits. The most famous stream is the Sagittarius stream. The Sagittarius dwarf elliptical galaxy is currently being cannibalized by the Milky Way. As it orbits our galaxy, the Milky Way's stronger gravity pulls on the near side of the dwarf harder than the far side. This difference in gravitational force, the tidal force, stretches the dwarf galaxy along its orbit. Stars get stripped from both ends, forming a stream that wraps completely around the Milky Way. The Sagittarius stream extends more than 360 Britam around the sky. It loops above the galactic plane, crosses through it, loops below, crosses again. If you could see the stream with your naked eye, it would appear as a faint band of light encircling the entire celestial sphere. But the stars are too dim and too spread out. Only large surveys mapping millions of stars across the sky can detect the stream's presence. Dozens of stellar streams have been discovered in the Milky Way's halo. Each one tells the story of a disrupted object. The GD1 stream comes from a destroyed globular cluster. The orphan stream has an unknown origin, its parent object completely gone. The Helmi stream marks an ancient dwarf galaxy merger that happened billions of years ago. New streams continue to be discovered as surveys become more sensitive and cover larger areas of sky. Stellar streams are valuable because they trace the Milky Way's gravitational field. Stars in a stream follow orbits determined by the galaxy's mass distribution. By measuring where stream stars are located and how they move, astronomers can reconstruct the gravitational potential they orbit within. This technique provides information about dark matter. Most of the galaxy's mass is dark matter, and streams respond to its gravity even though we cannot see the dark matter directly. Some streams show gaps or clumps, unexpected variations in stellar density along their length. These features might indicate the presence of dark matter subhalos, small concentrations of dark matter passing through the stream and gravitationally perturbing it. If confirmed, this would provide rare evidence for dark matter structure on small scales, testing tectons of how dark matter clumps and flows. The streams exist primarily in the halo because the disruption process happens when objects orbit through the galaxy's outer regions. Objects in the disk would be confused with the billions of disk stars, making streams impossible to detect. But in the halo, where the background stellar density is low, streams stand out. They are anomalies, linear structures in an otherwise sparse and roughly spherical distribution. Streams above and below the galactic plane cross through different environments than disk objects experience. They pass through the hot halo gas, the magnetic fields, the dark matter halo. Their orbits take them far from the plane, sometimes hundreds of thousands of light years out, then back down through the plane and out the other side. Each crossing exposes them to different conditions. The process of creating a stream takes time. A dwarf galaxy does not dissolve in a single orbit. It might survive dozens or hundreds of orbits, losing a little mass each time it passes near the Milky Way center, where tidal forces peak. The older streams are the most dispersed. Their stars spread so widely that detecting them becomes difficult. Younger streams are tighter, more coherent, easier to spot. Not all streams form from disrupted objects. Some might be birth streams, groups of stars that form together and remained loosely associated as they orbit the galaxy. These are harder to distinguish from tidal streams unless you can measure stellar ages and compositions. Birth streams would contain stars of similar age. Tidal streams would contain stars with a range of ages, because the parent galaxy or cluster forms stars over an extended period. The stellar streams prove the Milky Way is a cannibal. Our galaxy grew by eating smaller galaxies over billions of years. The streams are the remnants, the indigestible bones of the galaxies we consume. They orbit through the halo above and below us, ghostly rivers of stars, marking ancient violence. And the process continues. The Milky Way is still consuming dwarf galaxies today. New streams will form in the future. The cannibalism never stops. The Milky Way has dozens of satellite galaxies, small dwarf galaxies that orbit around us like moons around a planet. Most contain only millions of stars compared to the Milky Way's hundreds of billions. They are cosmic midgets, barely qualifying as galaxies at all, but their distribution is bizarre. Instead of spreading roughly spherically around the Milky Way, as theory predicted, they cluster in a thin plane perpendicular to the galactic disk. This satellite plane, sometimes called the disk of satellites, measures about 600,000 light-years across, but only 30,000 light-years thick. It stands nearly vertical relative to the Milky Way's stellar disk. About half of the known satellite galaxies orbit within this structure, all moving in roughly the same direction around the plane. The configuration is extremely unlikely to occur by chance. When astronomers first noticed this pattern in the 1970s, many dismissed it as a fluke, with only a few known satellites at the time. The sample size was too small to draw strong conclusions. But as more dwarf galaxies were discovered, the pattern persisted. The satellites really do prefer a plane, and that plane really is perpendicular to the disk. This contradicts expectations from galaxy formation theory. Satellites should orbit randomly, isotropically distributed around the host galaxy. Their orbits should reflect the chaotic mergers and interactions that built the galaxy over billions of years. A thin, planar distribution, especially one perpendicular to the disk, suggests something organized their orbits, and nobody knows what. Several theories attempt to explain the satellite plane. One suggests the satellites are not independent objects, but rather remnants of a larger galaxy that the Milky Way tore apart billions of years ago. The satellites would be fragments of that destroyed galaxy, still following orbits close to their parent galaxy's original path. This could create a planar distribution naturally. Another theory proposes the satellite plane formed from a cosmic filament, a large-scale structure in the dark matter distribution that fed galaxies into the Milky Way from a preferred direction. If satellites fell in along this filament, they would enter with similar orbital orientations, potentially creating a plane. A third possibility involves the Milky Way's dark matter halo. Recent research suggested the dark matter halo might be triaxial, shaped like a football or an egg rather than spherical. If the halo is elongated perpendicular to the disk, satellites orbiting in that direction would experience different gravitational forces than satellites orbiting in other directions. Over billions of years, this could preferentially preserve satellites in the perpendicular plane while disrupting satellites in other orbits. Most puzzling is the coherent rotation. Satellites do not just sit in the plane, they orbit around it, most moving in the same direction. This implies angular momentum, a spin to the system as a whole. Where did that spin come from? Random infall should produce no net rotation. The satellites should orbit both clockwise and counterclockwise in roughly equal numbers. The problem is not unique to the Milky Way. Andromeda, our nearest large galactic neighbor, also has a satellite plane. So do several other galaxies when examined carefully. This suggests the phenomenon is common, a natural outcome of galaxy formation processes we do not yet fully understand. Cosmological simulations are starting to reproduce planar satellite distributions in some cases, but the match between simulations and observations remains imperfect. For the Milky Way specifically, the satellite plane extends far above and below the galactic disk. If you traveled upward from the solar system perpendicular to the galactic plane, you would not encounter the satellite plane for tens of thousands of light years. But if you traveled sideways along a different perpendicular axis, you would intersect the satellite plane much sooner because it cuts across a different dimension of space. The satellites themselves are dying. Tidal forces from the Milky Way pull them apart over billions of years, stripping away their outer stars and leaving stellar streams like those described in the previous chapter. Eventually, each satellite will be completely destroyed, its stars absorbed into the Milky Way's halo. The satellite plane will fade as its members disappear. But for now, it persists, a perpendicular ring of dwarf galaxies orbiting around us, defying easy explanation. The dark matter halo surrounding the Milky Way might not align with the galactic disk. Recent evidence suggests the halo is tilted, possibly even perpendicular to the stellar disk. If true, this represents a major upheaval in the galaxy's structure. Sometime in its past, a reorientation of the entire dark matter distribution occurred, while the stars continued spinning in their original plane. Something massive must have happened to twist the halo. The evidence comes from multiple sources. Measurements of stellar motions in the halo show patterns inconsistent with a spherical or oblate dark matter halo aligned with the disk. The stars move as if responding to a gravitational field tilted relative to the disk. Precise mapping of satellite galaxy orbits also suggests the gravitational potential they orbit within is not symmetric around the disk's rotation axis. Computer simulations can reproduce tilted halos under specific conditions. If a large galaxy merges with the Milky Way, the merger can deposit angular momentum in a direction different from the disk's existing rotation. The dark matter, which dominates the galaxy's mass, responds to this new angular momentum by gradually reorienting itself. The stellar disk, being much lighter, cannot reorient as easily. It stays put while the dark matter halo tips around it. The process takes billions of years. The halo does not flip instantly. It gradually precesses and twists, with different parts of the halo at different distances from the galactic center reorienting at different rates. Eventually, the entire halo settles into a new configuration, perpendicular or highly inclined to the disk. The result is a galaxy with a completely misaligned dark matter distribution. Scientists propose that the Sagittarius dwarf galaxy merger could have triggered this tilting. Sagittarius is currently falling into the Milky Way, but it has orbited our galaxy for billions of years, passing through the disk multiple times. Each passage deposits energy and angular momentum into the halo. Over many orbits, this could have been enough to tilt the dark matter halo into a tilted configuration. The tilted halo explains several puzzles. The satellite plane perpendicular to the disk makes more sense if the dark matter halo is also perpendicular, because satellites respond primarily to dark matter gravity. The unusual properties of some stellar streams, which appear to orbit in directions inconsistent with a disk-aligned halo, also fit better with a tilted halo model. but the idea remains controversial. Measuring the dark matter halo's shape and orientation from inside the galaxy is extraordinarily difficult. Dark matter does not emit light, so we can only infer its properties from its gravitational effects on stars and gas. Those effects are subtle and require extremely precise measurements of stellar positions and velocities across large volumes of the halo. Recent papers suggested the tilt began 6 to 8 billion years ago, roughly half the age of the Milky Way. Before that time, the disk and halo were aligned as expected. Something happened around that epoch that initiated the tilt. The disk started tilting too, though more slowly than the halo. The galaxy's inner regions, where stellar gravity is strongest, retained some alignment. The outer regions tilted more dramatically. If the halo is indeed tilted perpendicular to the disk, it changes our understanding of the galaxy's structure. We cannot assume the disk and halo share the same symmetry. Forces acting above and below the disk would differ from forces acting in other directions. The gravitational potential becomes more complex, and objects orbiting through this tilted halo would experience unexpected perturbations. For the Oort Cloud, a tilted dark matter halo might affect long-term orbital stability. Comets at the solar system's edge orbit in the local gravitational field, which incides contributions from both the disk and the halo. If those two components point in different directions, the net force changes depending on where you are in space. Some comet orbits might be stabilized, others might be destabilized. The consequences remain unclear. The warped halo, if real, proves galaxies are dynamic structure. What you see in the stars does not necessarily reflect what exists in the dark matter. The two components can evolve independently, twisted by ancient mergers and interactions into titanics that seem impossible, but actually represent natural outcomes of gravitational physics operating over billions of years. The galactic disk is not a closed cis gas and energy escape continuously, blasted upward and downward by violent events in star-forming regions. Multiple supernovae exploding in the same area within a few million years create superbubbles that can break through the disk entirely. When a bubble breaches the surface, hot gas erupts into the halo like lava from a volcano. Astronomers call these eruptions galactic winds or chimneys, and they transport material thousands of light years above and below the galactic plane. The process begins in regions of rapid star formation. Dozens or hundreds of massive stars form in a single giant molecular cloud. These stars produce intense stellar winds, blowing gas away at thousands of miles. Within a few million years, the most massive stars explode as supernovae. Each blast adds energy to the expanding bubble, carved by stellar winds. The bubble grows, pushing aside surrounding gas and sweeping it into a dense shell. If the bubble forms near the galactic plane's midline, where gas is densest, the shell slows and eventually stalls. The bubble remains trapped in the disk. But if the bubble forms slightly above or below the midline, or if multiple bubbles merge, the combined structure can become buoyant, rising like a hot air balloon through the denser, cool gas of the disk. As the bubble rises, it encounters less resistance. The gas density decreases exponentially with height above the plane. What started as a difficult climb accelerates into a breakout. The bubble breaches the disk's upper boundary and erupts into the low-density halo. Hot gas streams outward at hundreds or thousands of miles LS, carrying with it metals forged in the stars that created the bubble. These galactic chimneys are visible in radio and X-ray observations as vertical structures extending from the disk into the halo. The gas inside is hot, ionized, and enriched with elements heavier than helium: oxygen, carbon, nitrogen, iron. All the products of stellar nucleosynthesis get transported upward. Without this process, metals would remain locked in the disk where they formed. The halo would be pristine, containing only hydrogen and helium from the Big Bang. But observations show the halo gas contains metals not as much as the disk, but more than it should, if winds never escaped. The galactic wind mechanism explains this enrichment. It also explains where the energy heating the halo gas comes from. Supernovae in the disk deposit energy into bubbles that escape into the halo, heating and stirring the hot coronal gas that fills the space above and below. The Aquila supershell is one example. This enormous structure extends at least 550 light-years into the halo, driven by star formation and supernovae in a region near the Aquila constellation, as seen from Earth. The Cygnus superbubble is another, with a diameter of 450 light-years carved by stellar activity in the Cygnus region. These are local examples, but similar structures probably exist throughout the Milky Way. Wherever vigorous star formation occurs, galactic winds are bipolar. They flow both upward and downward from the disk, creating a symmetry perpendicular to the plane. The outflows follow paths of least resistance, which tend to be along the vertical axis, where gas density drops fastest. Some wind material escapes the galaxy entirely, lost to intergalactic space. Other material falls back, raining down onto the disk after millions of years, completing a galactic fountain cycle. The escaped gas carries angular momentum away from the disk. This momentum loss affects the disk's rotation over billions of years. Simulations suggest galactic winds play a role in regulating star formation by removing gas that would otherwise collapse to form new stars. Winds also enrich the intergalactic medium with metals, seeding the space between galaxies with elements that can be incorporated into new galaxies forming later. For us in the solar system, galactic winds are distant phenomena. We sit too far from any major star-forming regions to feel direct effects. But billions of years ago, when the Sun formed, it might have been born inside a star-forming region similar to those that create galactic wind. The early solar system could have been bathed in hot, metal-enriched gas from nearby supernovae. That gas contributed to the solar nebula from which planets formed. The chimneys above and below us carry the galaxy's blood into space. They transport matter and energy from the dense, fertile disk into the empty halo. They connect the visible galaxy to its invisible surroundings. And they prove that what lies above and below is not just empty space, but a dynamic environment shaped by violence from below. When scientists measured the temperature of the hot gas inside the local bubble, using the Rosetta X-ray telescope, they discovered something nobody predicted. The gas is significantly cooler when looking toward the North Galactic Pole compared to looking toward the South Galactic Pole. The difference is measurable, repeatable, and completely unexplained. Nobody knows why the local bubble has a temperature gradient. The northern side measures roughly 700,000 degrees Kelvin. The southern side reaches about 1 million degrees, or slightly higher. That is a substantial difference. Nearly 50% hotter on one side than the other. For a structure as large as the local bubble, spanning 1,000 light-years, such a temperature asymmetry suggests something created unequal heating between the two hemispheres. One possibility is that the supernovae that created the bubble did not explode symmetrically. If more stars exploded on the southern side, or if they exploded more recently on that side, the gas there would have been heated more intensely. The temperature difference would be a relic of the asymmetric explosion pattern frozen into the bubble structure. Another theory suggests the surrounding interstellar medium was not uniform before the bubble formed. The local bubble expanded into pre-existing gas with different properties in different directions. If the gas to the south was denser or had different composition, it might have responded differently to the shock waves from supernovae, resulting in different final temperatures. A third possibility involves recent activity. Perhaps a late supernova exploded on the southern side within the last few million years, adding extra heat to that hemisphere without having time to equilibrate across the entire bubble. The temperature gradient would be temporary, gradually evening out over the next 10 or 20 million years as the hot gas mixes. The uncertainty about the cause reflects how poorly we understand even nearby structures. The local bubble surrounds us. We live inside it, yet we cannot explain its basic temperature profile. The problem is that we see the bubble from only one vantage point, from inside looking outward. We cannot move to a different location and observe how the temperature varies from other directions. Temperature measurements rely on analyzing X-ray spectra. Hot gas emits X-rays with energies that depend on the gas temperature. By measuring which X-ray energies are present and their relative intensities, astronomers can determine the temperature of the emitting gas. The Erasita telescope observed the entire sky in X-rays, creating a full sky temperature map of the local bubble's interior. That map clearly shows the north-south asymmetry. The feature is real, not a measurement artifact or instrumental effect. Multiple analysis methods confirm the gradient exists. But what creates it? Until we develop better models of superbubble formation and evolution, or until we discover additional observational clues, the temperature gradient remains a mystery. The asymmetry might affect how the bubble expands in different directions. Hotter gas has higher pressure and expands faster. If the southern side is hotter, it might be expanding more rapidly than the northern side. This could create a lopsided structure, with the bubble's center offset from where the initial supernova exploded. Over time, the entire bubble might drift northward as the hotter southern side pushes it in that direction. For the solar system, the temperature gradient probably has no immediate consequences. We sit inside the bubble, but are insulated from direct exposure to the hot million-degree gas by the denser local interstellar cloud surrounding us. The cloud acts as a buffer, protecting the heliosphere from the extreme temperatures of the bubble's interior. But the gradient does affect the larger environment we inhabit. If future supernova explosions occur within the local bubble, they will interact with gas that already has a temperature gradient. The new explosions might amplify the asymmetry or erase it, depending on where they occur. The bubble's future evolution depends partly on its current temperature structure, which we still do not fully understand. The unexpected temperature gradient is a reminder that space is more complex than models predict. Even large-scale structures show surprises when examined closely. The local bubble has been studied for decades, yet only with the telescope's unprecedented sensitivity did the temperature asymmetry become clear. What other surprises hide in the data, waiting for better instruments to reveal? Every second, hundreds of high-energy particles slam into Earth's atmosphere from above and below. These cosmic rays, despite their name, are not rays at all. They are atomic nuclei, mostly protons, accelerated to nearly the speed of light by violent processes across the galaxy. They rain down on Earth continuously, invisible and unstoppable. Where they come from and how they reach such enormous energies remain partially mysterious. Cosmic rays were discovered in 1912 by Victor Hess during balloon flights into the upper atmosphere. He measured increasing levels of ionizing radiation at higher altitudes, proving the radiation came from space rather than Earth. The discovery eventually earned him a Nobel Prize, but more than a century later, scientists still debate the sources and acceleration mechanisms for the highest energy cosmic rays. Most cosmic rays come from supernova remnants. When a star explodes, the blast wave expanding outward accelerates particles to relativistic speeds. The shock front acts like a cosmic particle accelerator, bouncing particles back and forth across the shock until they gain enormous energies. This mechanism, called diffusive shock acceleration, can produce cosmic rays with energies up to about 100 trillion electron volts. But some cosmic rays have higher energies, much higher. The most energetic cosmic ray ever detected hit Earth's atmosphere, with energy equivalent to a baseball traveling 60 miles per hour, all concentrated in a single atomic nucleus. Nobody knows how natural processes can accelerate particles to such ridiculous energies. Supernova remnants cannot do it. Even the most powerful sources in the galaxy struggle to explain the highest energy cosmic rays. Cosmic rays do not travel in straight lines from their sources to Earth. The galaxy's magnetic fields deflect charged particles, causing them to wander through space in random zigzag paths. A cosmic ray might travel thousands of light years through the galaxy, bouncing around magnetic field structures before eventually reaching the solar system. By the time it arrives, its direction of motion no longer points back toward its source. The particle has lost all memory of where it came from. This makes identifying sources difficult. Astronomers can detect where cosmic rays arrive from, but those arrival directions are randomized by magnetic fields. Only at the very highest energies, where magnetic deflection becomes weaker, can cosmic rays travel nearly straight, potentially allowing their sources to be identified. But particles at those energies are extremely rare. Detectors wait years to observe a single event. When cosmic rays hit Earth's atmosphere, they collide with nitrogen or oxygen nuclei, creating showers of secondary particles. These showers cascade down through the atmosphere, multiplying with each collision until thousands or millions of particles reach the ground from a single cosmic ray. Detectors on the surface measure these showers, reconstructing the energy and type of the original cosmic ray from the shower properties. The cosmic ray flux varies depending on the sun's activity. During solar maximum, when the sun produces strong magnetic fields and intense solar wind, fewer cosmic rays penetrate to Earth because they get deflected by the enhanced interplanetary magnetic field. During solar minimum, the solar wind weakens and cosmic ray flux increases. Earth's atmosphere experiences about 20% more cosmic rays during solar minimum than solar maximum. Cosmic rays have consequences. They ionize the upper atmosphere, creating electrical conductivity that affects atmospheric chemistry. Some researchers suggested cosmic rays might influence cloud formation by creating ionization that helps water vapor condense. If true, variations in cosmic ray flux could affect climate over long time scales, though the effect would be subtle compared to other climate drivers. Living organisms on Earth's surface are protected from cosmic rays by the atmosphere, which absorbs most of the incoming radiation. But astronauts in space receive much higher doses. On the International Space Station, cosmic ray exposure is about 150 times higher than on the ground. On a trip to Mars, exposure would be even greater. Cosmic rays represent one of the major health risks for long-duration space missions. The cosmic ray background also affects technology. High-energy particles passing through computer chips can flip individual bits, causing soft errors in memory or logic circuits. Spacecraft and satellites experience these errors regularly. Cosmic rays create false signals in detectors, limiting the sensitivity of astronomical instruments. Even elections have been blamed on cosmic rays when voting machines malfunctioned. Above and below the solar system, cosmic rays fill all of space. They arrive from every direction, accelerated by supernovae, pulsars, supermassive black holes, and possibly other sources we have not identified. They carry information about the most violent processes in the galaxy, and they rain down on us constantly, invisible travelers from the depths of space, bringing energy from explosions that happened thousands of years ago, in places thousands of light years away. There is a line in space beyond which nothing can remain bound to the sun. Not planets, not comets, not spacecraft. At this boundary, the Milky Way's gravity becomes stronger than the sun's. Objects beyond this line belong to the galaxy, not to our solar system. This is called the tidal truncation radius, and it marks the absolute edge of our solar system's gravitational dominance. That edge sits somewhere between 100,000 and 200,000 astronomical units from the sun. The boundary exists because gravity weakens with distance. Close to the sun, solar gravity dominates overwhelmingly. The sun pulls on nearby objects far more strongly than the galaxy does, but move outward, and the sun's pull weakens rapidly. Meanwhile, the galaxy's tidal forces stay roughly constant because the scale of the galaxy is so much larger than the solar system. At some distance, the two forces become equal. Beyond that distance, the galaxy wins. But the idea remains controversial. Measuring the dark matter halo's shape and orientation from inside the galaxy is extraordinarily difficult. Dark matter does not emit light, so we can only infer its properties from its gravitational effects on stars and gas. Those effects are subtle and require extremely precise measurements of stellar positions and velocities across large volumes of the halo. Recent papers suggested the tilt began 6 to 8 billion years ago, roughly half the age of the Milky Way. Before that time, the disk and halo were aligned as expected. Something happened around that epoch that initiated the tilt. The disk started tilting too, though more slowly than the halo. The galaxy's inner regions, where stellar gravity is strongest, retained some alignment. The outer regions tilted more dramatically. If the halo is indeed tilted perpendicular to the disk, it changes our understanding of the galaxy's structure. We cannot assume the disk and halo share the same symmetry. Forces acting above and below the disk would differ from forces acting in other directions. The gravitational potential becomes more complex, and objects orbiting through this tilted halo would experience unexpected perturbations. For the Oort cloud, a tilted dark matter halo might affect long-term orbital stability. Comets at the solar system's edge orbit in the local gravitational field, which incides contributions from both the disk and the halo. If those two components point in different directions, the net force changes depending on where you are in space. Some comet orbits might be stabilized, others might be destabilized. The consequences remain unclear. The warped halo, if real, proves galaxies are dynamic structure. What you see in the stars does not necessarily reflect what exists in the dark matter. The two components can evolve independently, twisted by ancient mergers and interactions into titanics that seem impossible, but actually represent natural outcomes of gravitational physics operating over billions of years. The galactic disk is not a closed cyst. Gas and energy escape continuously, blasted upward and downward by violent events in star-forming regions. Multiple supernovae exploding in the same area within a few million years create superbubbles that can break through the disk entirely. When a bubble breaches the surface, hot gas erupts into the halo like lava from a volcano. Astronomers call these eruptions galactic winds or chimneys, and they transport material thousands of light years above and below the galactic plane. The process begins in regions of rapid star formation. Dozens or hundreds of massive stars form in a single giant molecular cloud. These stars produce intense stellar winds, blowing gas away at thousands of miles. Within a few million years, the most massive stars explode as supernovae. Each blast adds energy to the expanding bubble carved by stellar winds. The bubble grows, pushing aside surrounding gas and sweeping it into a dense shell. If the bubble forms near the galactic plane's midline, where gas is densest, the shell slows and eventually stalls. The bubble remains trapped in the disk. But if the bubble forms slightly above or below the midline, or if multiple bubbles merge, the combined structure can become buoyant, rising like a hot air balloon through the denser, cool gas of the disk. As the bubble rises, it encounters less resistance. The gas density decreases exponentially with height above the plane. What started as a difficult climb accelerates into a breakout. The bubble breaches the disk's upper boundary and erupts into the low-density halo. Hot gas streams outward at hundreds or thousands of miles LS, carrying with it metals forged in the stars that created the bubble. What happens at the tidal truncation radius? Objects orbiting the Sun at that distance feel equal gravitational tugs from the Sun and from the galactic tide. Their orbits become unstable. Small perturbations, which closer in would cause only minor orbital changes, now can eject objects entirely. Over millions of years, the galaxy strips away any objects orbiting near or beyond the truncation radius. This is why the Oort cloud has an outer edge. Comets cannot survive beyond the tidal truncation radius for billions of years. The galaxy removes them. The outer boundary of the Oort cloud, at roughly 200,000 astronomical units, coincides with where the tidal truncation radius is calculated to be. It is not a coincidence. The galaxy itself defines where our solar system ends. The exact location of the boundary depends on which direction you look. Toward the galactic center, tidal forces are slightly stronger, bringing the truncation radius closer. Away from the galactic center, tidal forces weaken slightly, allowing the boundary to extend farther. The Oort cloud is not a perfect sphere. It is slightly elongated, stretched along the line pointing away from the galactic center, where solar gravity can hold objects at greater distances. Calculating the tidal truncation radius requires knowing the galaxy's mass distribution, including both visible and dark matter. Uncertainty in the dark matter halo's properties translates directly into uncertainty in where the boundary sits. Different models place it anywhere from 100,000 to 200,000 astronomical units, a factor of 2 range that reflects our incomplete knowledge of galactic structure. Beyond the tidal truncation radius lies interstellar space, not just in the sense of being outside the heliosphere, but in the deeper sense of being outside the sun's gravitational domain. Objects there do not orbit the sun. They orbit the galactic center, influenced primarily by galactic gravity. If the sun has objects beyond the truncation radius, they are not part of the solar system anymore. They are independent interstellar objects that happen to be passing near the sun temporarily. The concept applies to all stars. Every star has its own tidal truncation radius, beyond which the galaxy dominates. Stars in dense regions near the galactic center have smaller radia because nearby stars contribute additional tidal forces. Stars in the halo, far from the galactic center, have larger radia because local tidal forces are weaker there. The sun's truncation radius is typical for a star at our galactic location. Some scientists speculated that the sun might have had a much more extensive Oort cloud initially, perhaps extending several times farther than it does now. Encounters with passing stars and gradual erosion by galactic tides stripped away the outermost comets over billions of years. What remains is the inner core of the original cloud, the region close enough to the sun that even after 4.2 billion years, solar gravity still holds it. The tidal truncation radius marks the final frontier, the true edge of the sun's dominion. Beyond this invisible line, you are no longer held by the sun's gravity. You belong to the galaxy itself. Everything that stretches above and below the solar system, every vast structure described before, exists beyond this limit, or operates on scales far greater than it. The local bubble extends roughly 1,000 light-years. The galactic halo reaches hundreds of thousands more, and antiming it all, dark matter forms a ghostly scaffold around the Milky Way. Our solar system is a speck within these immense cosmic layers. The sun's gravitational reach fades after just 3 light-years. Beyond that, the Milky Way assumes control. What surrounds us is not emptiness, it is a galactic ocean of hot gas, magnetic fields, dark matter, cosmic rays, stellar rivers, and ancient relics forged over billions of years. We drift within this vastness, sheltered for now by the sun's fragile sphere of influence. But the boundary is real. The sun's reign ends there, and beyond that edge, the galaxy awaits.